Welcome back to Intuitive Epidemiology. In today's video, we will discuss immortal time bias. My name is Taylor, and I am a PhD-trained epidemiologist living in Vancouver. And let's dive into the video. As discussed in past videos, epidemiology can be broken down into three broad analytical approaches. The first, which is description. The second area relates to prediction. And the area that we will focus on today relates to explanation in epidemiology. In this area, we can examine a relationship between a given exposure and an outcome. And a hypothetical research question could be, is treatment A versus treatment B associated with survival? In this case, our exposure is a hypothetical treatment, and our outcome is death. Our finding could be an estimate, quantifying the association or the relationship between treatment A versus treatment B and death. And our estimate, more specifically, is known as a measure of effect. And there are various measures of effect that we can estimate in epidemiology, which include, but are not limited to, odds ratios, risk ratios, rate ratios, and hazard ratios. In terms of odds ratios and risk ratios, I've shown you this 2x2 table in past videos. I describe these measures of effect as involving a simple counting and comparing exercise, where we can ask ourselves how many treated people did versus did not experience the outcome, and how many untreated people did versus did not experience the outcome under study. Odds ratios can be viewed as asking the question how often something happens in our exposed versus our unexposed groups. These are the hand calculations that you could derive from this 2x2 table for both the odds ratio measure of effect as well as the risk ratio measure of effect. And just so we're all on the same page, going back to our research question, is treatment A versus treatment B associated with survival? If we were to estimate an odds ratio or a risk ratio of 1, this would mean that the treatment has no impact on one's likelihood of death. If you were to estimate an odds ratio or a risk ratio greater than 1, this would indicate that the treatment increases the likelihood of death. And in contrast, if we were to estimate an odds ratio or a risk ratio less than 1, this would indicate that the treatment decreases the likelihood of death. So these measures of effect, odds ratios and risk ratios, can also be estimated using models, or more specifically, logistic regression for odds ratios, or log binomial models for risk ratios. However, you may be asking yourself the question, aren't we going to be talking about a time-related bias in this video? And as I've just recapped, it is unclear where time is being considered when estimating both odds ratios and risk ratios. So while there is an implicit time component in most analyses, including analyses that estimate odds ratios and risk ratios, such as participant enrollment dates, ends of follow-up, dates of exposures, dates of outcomes, and so on, the estimation of odds ratios and risk ratios does not explicitly incorporate time. In other words, when looking at the 2x2 tables that I showed you in the previous slides and in past videos, there were no time-related components in the calculations. And if you were to prepare data where you would fit a logistic or a log binomial regression model in order to estimate odds ratios or risk ratios, you would not explicitly have to include a time-related variable. Or more specifically, there are no person-time related variables specified for the denominators when estimating the parameters from these models. However, going back to our measures of effect, there are also rate ratios and hazard ratios which are commonly estimated in epidemiologic studies. And unlike odds ratios and risk ratios, rates and hazards explicitly consider time. So while we can view odds and risks as telling us how often something happens in our exposed versus our unexposed groups, rates and hazards can tell us how quickly something happens in our exposed versus our unexposed groups. So we can take our familiar 2x2 table and edit it to now look at the number of outcomes, or the number of deaths, in our treated and our untreated groups, as well as the total person time at risk in both of these groups. In other words, the total person time before death. Before we dive into that new version of the 2x2 table, let's discuss person time. So person time at risk is the actual time at risk in days, months, or years that a participant contributes to a study. Now we know from a figure such as this one that people can be followed for different lengths of time in a study. For example, in this figure, there are 12 people who are followed for up to 34 months of person time before their deaths. And it's important to know that time at risk is only counted prior to the occurrence of the outcome occurring under study. And therefore, while the person is still at risk of developing the outcome. So in our example, total person time at risk is the total person time in days, months, years, or so on that is experienced by a person before they experience the outcome under study, which in this case is death. So now we can think of person time in terms of treated versus untreated participants, or exposed versus unexposed people. In this diagram, we have 5 different people. Person 1 and person 3 are untreated, and person 2, 4, and 5 are treated. They are followed for a different number of days until they pass away. And for simplicity, we're going to assume that everybody is treated or not on day 0, and every participant dies at some point during the 70-day window. So, as noted, there were 3 deaths among the treated participants. Person 2 passed away at 70 days. Person 4 also passed away after 70 days. And person 5, who was also treated, passed away at 53 days. Therefore, the total person time at risk, or the person days before death, experienced in the treated group is 70 days plus 70 days plus 53 days for a total of 193 person days. We could do a similar exercise for the 2 deaths among the untreated people, person 1 and person 3, where 19 person days were experienced before death for untreated person 1, and 24 days were experienced before person 3, who was also untreated, passed away, for a total of 43 person days before. Now we can go back to the new version of our 2x2 table, where we have our exposure, treated versus untreated. In this example, our outcome that we can use to calculate rates, the number of deaths in each of these groups, as well as the total person time at risk in both the treated group and the untreated group. 193 person days for those who were treated, and 43 person days for those who were untreated. And of course, as mentioned, everybody was either treated or untreated at enrollment or day 0. Now, a rate in the treated group is the number of deaths in the treated group divided by the total treated person time before death. We could similarly estimate a rate in the untreated group, which is the number of deaths in that group, divided by the total untreated person time before death. So, to calculate this first rate, the rate of death in the treated group, we would do 3 deaths divided by 193 person days. Now this comes out to 0.0155 deaths per person day in the treated group. Now it's a bit difficult to think of deaths in terms of 0.0155 deaths. Therefore, what we typically do in epidemiology is multiply this rate by 10, 100, or 1,000, sometimes even by 10,000 when the outcome is very rare. And if we were to multiply this death rate by 1,000, in this case, we would get 15.5 deaths per 1,000 person days. We could do a similar calculation down below. 2 divided by 43 person days, 0.0465 deaths per person day. Multiply this by 1,000, giving us a death rate of 46.5 deaths per 1,000 person days. And what we can see here is that the death rate is much lower in the treated group as compared to the untreated group. Now, remembering that our measure of effect is in fact a rate ratio in this example, which tells us how quickly something happens in our exposed and our unexposed groups, we can divide these two rates by each other. So we have our rate in our treated group, 3 divided by 193, or 15.5 deaths per 1,000 person days. And we also have our rate in our untreated group, 2 divided by 43, or 46.5 deaths per 1,000 person days. If we divide 15.5 by 46.5, we get a rate ratio of 0.33. Similarly to odds ratios and risk ratios and their interpretations, a rate ratio less than 1 indicates that the treatment reduces the death rate, that the rate of death is lower in the treated group as compared to the untreated group. However, unlike odds and risks, or unlike odds ratios and risk ratios, rates explicitly consider time, or more specifically, person time. So the literal interpretation of this rate ratio is that people who were treated had 0.33 times the rate, or a lower rate of dying compared to people who were untreated. In this case, assuming no bias whatsoever, the treatment is in fact beneficial at reducing the rate of dying. For the purposes of this talk, hazard ratios, another commonly estimated measure of effect, also tell us how quickly something happens in our exposed versus our unexposed groups. However, for simplicity, you can think of hazards as an instantaneous rate. Therefore, everything we've discussed regarding rate ratios and person time can also be thought of in the context of hazards and hazard ratios. Now, as we discussed with odds ratios and risk ratios, we can also think of rate ratios and hazard ratios in the context of regression models, where rate ratios can be estimated using Poisson regression, and hazard ratios, as an example, can be estimated using Cox proportional hazards models. And in these cases, it's very important to explicitly consider time-related biases, and this would include immortal time bias, the main focus of this video today. So now that we are done with the introduction to rates, hazards, and person time, we can dive into immortal time bias. But first, it's important to know that a bias in general is any systematic error in an epidemiologic study that results in an incorrect estimate of the association between an exposure and an outcome. And that measures of effect include odds ratios, risk ratios, and in the context of immortal time bias, we will focus on rate ratios and hazard ratios. So what is immortal time bias? Immortal time bias is the inappropriate accounting of immortal person time. And I'm going to use the following peer-reviewed publication titled Problem of Immortal Time Bias in Cohort Studies, example using statins for preventing progression of diabetes, as a source of information for the remainder of this video. This paper was published in 2010 in the BMJ by Levesque and colleagues, and since then has been cited over 660 times. Now we will move on to defining immortal time. And we're going to define immortal time and break down immortal time bias by unpacking what is the first main paragraph of the Levesque and colleagues paper. So Levesque refers to immortal time as person time during which, by design, death or the study outcome cannot occur. So immortal time refers to person time during which, by design, death or the study outcome cannot occur. As you can imagine, this is much easier to depict using a diagram, and I would like to credit catalogofbias.org, a fantastic resource on many biases, for providing the figures that I have modified for this video. So going back to the Levesque paper, this team indicates that immortal time arises when the determination of an individual's treatment status involves a delay or wait period during which follow-up time is accrued. And this is shown below. So an individual could be diagnosed with a given disease or condition, and a period of time could pass before they receive the hypothetical treatment that is meant to help them with their ailment. So this time between finding out a person has a disease and getting the treatment for that disease is referred to as immortal time. Now, why is this the case? The wait period is considered immortal because individuals who end up in the treated group, or individuals who end up getting the prescription to treat their disease, have to survive, be alive, and be outcome free until the treatment is received. If somebody has the outcome, whether that's death or another outcome that you're examining, before they take up the treatment, they are assigned to the untreated group. Now, this is much easier to visualize in this diagram. Now we have a person who has been categorized or coded as treated, as well as an untreated individual. Both of these folks are diagnosed with a given condition. This person goes on to get a prescription filled that is meant to help them with their condition, and then at some point later on, they pass away, which in our example is the study outcome. Now, in order for this person to have this experience depicted in this figure, they must survive and not experience the outcome, which just also happens to be death in our example, until the point of receiving their prescription. If this individual were to pass away before receiving their prescription, they would look like this in the data. A person that experiences the outcome or dies before receiving the treatment, which in this case is a prescription, will be coded or classified as untreated in this figure. And quite clearly, a treated person cannot die before their prescription fill, or else they are coded as untreated in this schematic. And this is why this period of time in between the date of diagnosis and the date of the prescription filling is referred to as immortal time. Immortal time bias is introduced when this period of immortality, in quotes, is either misclassified with regards to the treatment status or is excluded from the analysis altogether. So there's two causes of immortal time bias. One relates to the misclassification of immortal time, and the other relates to the exclusion of immortal time. In the first scenario, immortal time is inserted or misclassified into the denominator of the rate for the treated group. In the second scenario, immortal time is excluded from the denominator of the rate for the untreated group. And in both of these scenarios, immortal time bias is introduced. Before I show you how this comes to be, it's important to note that immortal time bias is particularly problematic because it necessarily biases the results in favor of the treatment under study. And it does this by conferring a spurious survival advantage to the treated group. In other words, immortal time bias can make a given treatment look beneficial when such a treatment is in fact unhelpful or even harmful. And this is why immortal time bias is so problematic in the epidemiologic literature. Before we discuss the implications of immortal time bias in the calculation of rates, let's go through this hypothetical example when focusing on this particular denominator. As a reminder, a rate ratio is the rate in the treated group of the outcome under study, which in our case is death. So it's the death rate in the treated group divided by the death rate in the untreated group. On this slide, let's focus on the denominator for the rate in the treated group in this orange box. So what happens if this treated denominator is increased? What happens if we add more person days to the total treated person time before death? If more time passes before death occurs, we will have a decreased death rate, a decreased rate of death in the treated group. So let's walk through this in a simple mathematical calculation. As we previously discussed, we had 3 deaths per 193 person days in our first example calculation. And this led to a death rate in the treated group of 15.5 deaths per 1,000 person days. Now, what happens if we add 100 person days to this denominator? We then have 3 deaths per 293 person days, which gives us a death rate in the treated group of 10.2 deaths per 1,000 person days. Again, showing this numerically, we first had 3 deaths divided by 193 person days, and now we have 3 deaths divided by 293 person days. So in the first scenario, our rate ratio was 15.5 divided by 46.5, which gave us the rate ratio of 0.33. But if we add 100 person days to the denominator for our rate treated, we get a lower death rate in our treated group and an overall lower rate ratio of 0.22. What this shows us is now in this scenario, the treatment appears even more beneficial than it previously did. Now, let's bring this example back to the context of immortal time and immortal time bias. So we have to ask ourselves the question, what happens when you increase the denominator of the rate for the treated group, as we just did on the previous slides, while also ensuring that the outcome cannot occur? Again, as we mentioned, this individual during this period of time cannot die or experience the study outcome. This example is simplified because death just so happens to be the study outcome. However, as we know, if this person were to pass away in this period, they would not have went on to receive the treatment, which in this case is a prescription. Therefore, by definition, this is referred to as immortal time. So these person days, however many days or months this is, are referred to as immortal time. So what happens when you increase the denominator of the rate for the treated, which is what you would do if you took these immortal days and put them down here and counted them in this denominator? What happens when you do that while ensuring the outcome cannot occur, which is what happens during this period? They cannot die or they will not receive their prescription. This is in fact the definition or the textbook example of misclassifying immortal time into your rate calculation. So what you've now done is you've biased your rate ratio through immortal time bias. You've erroneously estimated a stronger beneficial effect of your treatment than is in fact true by misclassifying immortal time into the denominator of your rate for the treated before calculating your overall rate ratio. Now, this is the same diagram or figure from the Levesque and colleagues paper, just again showing that when you misclassify this immortal time, or this time between the date of diagnosis and the date of the treatment, which in this case is a prescription, you bias your rate ratio through immortal time bias, and you erroneously estimate a stronger protective effect or a lower rate ratio than is in fact true. So obviously, the next question is, how can we avoid immortal time bias, which is the inappropriate accounting of immortal person time? So we have the biased approach to accounting for person time, where we have immortal time, the time between the diagnosis and the date of the treatment, being classified as treated person time. The unbiased approach to classifying person time is to actually treat this period, the time between being diagnosed and having the prescription filled, as untreated person time. All to say, what this means is that the unbiased approach, or the correct approach to accounting for person time, is thinking in terms of person time and not in terms of people. In other words, a person is not treated or untreated, but a person experiences treated and untreated person time. Another way to look at this is in the context of time fixed versus time dependent analyses. A biased analysis is known as a time fixed analysis. And in this case, in the biased approach, you consider ever treated participants as always treated. This individual, yes, was treated at some point in time, but they only received the treatment as of this point. Therefore, classifying the entire follow-up duration into the treated group, including this immortal time, is incorrect. So what you do not want to do is classify the person time prior to the receipt of treatment towards this denominator. You do not want to put this time, this immortal time, prior to receiving the prescription in the denominator for the rate. What you want to do is classify the untreated time for this ever treated person into the untreated group. So a time-dependent approach to this analysis allows ever treated people to contribute untreated person time. So that person time prior to the receipt of treatment is actually counted appropriately towards the total untreated person time before death denominator, which is this denominator right here. Now, if we go back to the main introductory paragraph in the Levesque paper, we can recall that immortal time bias is introduced when this period of immortality is either misclassified with regards to the treatment status or excluded from the analysis. And what we've primarily focused on thus far is the misclassification of the immortal time into the denominator of the rate for the treated group. However, immortal time bias is also introduced when this time is erroneously excluded from the denominator. Now, going back to the figure in the Levesque paper, we can recall that the unbiased or the time-dependent approach allows us to treat the ever-treated people as being untreated before they receive their first prescription. In other words, the person time prior to the receipt of treatment is actually meant to be counted as untreated person time. Therefore, while the gut reaction to fixing the misclassified immortal time is to exclude the immortal time from your entire analysis, this is also incorrect and will also introduce immortal time bias but in a slightly different manner. Here, the Levesque paper visually depicts the second cause of immortal time bias, which is the exclusion of immortal time. In order to understand this, we can go back to our rate ratio formula and focus on a different denominator. In this case, we're focused on the rate, or the death rate in our case, of the untreated group, and the denominator of the total untreated person time before death. And we can ask ourselves a similar question. What happens when you decrease the denominator of the rate for the untreated group by inappropriately excluding this person time altogether? So what happens when you have less untreated person time being counted down here than you should, or less person days being attributed or accounted for in this denominator? What you see is an increased rate of death in the untreated group. The fewer person days you have in this denominator, the higher the rate will be. Therefore, again, but for different reasons, you've biased your rate ratio by immortal time bias. You've erroneously estimated a stronger beneficial effect of the treatment than is in fact true. You've caused the same bias, but in a different way. Now, wrapping up this line of thinking, there are two causes of incorrect denominators for your rates. Therefore, there's two ways you can estimate a biased rate ratio. The first is by misclassifying your immortal time. The second is by excluding immortal time. In the first case, you're misclassifying immortal time into the denominator of your rate for your treated group. So what happens here is you have a biased rate in your treated group that is in fact underestimated. The rate in the treated group is too low. In our example, the death rate in the treated group is too low when you misclassify this immortal time. When you exclude the immortal time, the death rate is too high. It's overestimated. If the rates are biased, if the individual death rates in the treated and the untreated groups are wrong, your rate ratio that you calculate using these rates will also be wrong. And in this case, it's wrong because of immortal time bias. Now, the Levesque paper uses another study to demonstrate the impacts of immortal time bias, or the consequences of immortal time bias. So in the Levesque BMJ paper, they demonstrate this bias by replicating the Yi et al. Statin study using the same data from Saskatchewan. Levesque says they demonstrate and quantify the immortal time bias by replicating the time-fixed or time-independent analysis used by Yi et al. And then they did a simple time-dependent or corrected analysis to see what would happen when you properly account for person time. So they first estimated rate ratios using Poisson regression, where they did and did not properly account for immortal time. And they also estimate hazard ratios using Cox proportional hazards models. So the Yi et al. Paper looks at the relationship between statin use in type 2 diabetes and its association with a delay in starting insulin. Now, this example in the Yi paper is slightly complicated in the sense that they're looking at the relationship between statin use for cardiovascular disease and diabetes progression. So the exposure in the original paper that is being replicated is statin use, and the outcome is diabetes progression as being captured through the starting of insulin. So insulin is typically only used for people who have diabetes when oral anti-hyperglycemics are not working well enough. So in the Yi paper, they say that diabetes progression, or the worsening of diabetes, can be captured when seeing somebody transition from oral anti-hyperglycemics to the starting of injectable insulin. Now, what you would initially think from such an analysis is that those who are on statins and they're being used to treat some sort of cardiovascular disease-related events would be at higher risk of diabetes progression because cardiovascular health in and of itself is a risk factor. Poor cardiovascular health, rather, is a risk factor for diabetes progression. So this sets the clinical stage for the Yi et al. Paper, and Levesque and colleagues in the Immortal time bias paper use Poisson regression to estimate rate ratios using the time fixed or biased approach, which was done by Yi et al. And they also use a time-dependent analysis to correct for Immortal time bias. And similarly, because the appropriate accounting of person time is also important for hazard ratios, Levesque and colleagues also used Cox models to estimate hazard ratios in a time-fixed or biased manner, as well as a time-dependent manner, where again, Immortal time bias was properly accounted for. Now, this is table 2 in the Levesque and colleagues paper, where they have the biased time-fixed analysis at the top of the table, and this is the results you would have seen in the original Yi et al. Paper, as well as the unbiased or time-dependent analyses. In the biased analysis, Immortal person time is misclassified into the denominator for the treated group. And in this case, they estimate a crude rate ratio of 0.84. So what they're seeing in the biased or time-fixed analysis is a rate ratio less than 1, indicating that statin use is protective against diabetes progression, or that being on statins lowers the rate of progressing to more severe diabetes. And they see a similar answer when estimating a hazard ratio using a Cox model while not appropriately accounting for Immortal time. What they do in the time-dependent analysis is correct for Immortal time by appropriately classifying the Immortal time into the untreated group. And what is interesting is they get entirely different measures of effect that are in the exact opposite direction. So now you see a rate ratio of 2.68 and a hazard ratio of 1.97. In the biased or time-fixed analysis, where Immortal time was not appropriately handled, they observed that statin use was a protective factor against diabetes progression. And in the unbiased analysis where immortal time was appropriately accounted for, they found that being on statins increased your rate of progressing to more severe diabetes, which was much more in line with what you would expect clinically and substantively based on your understanding of why people take statins to begin with. Now, before we wrap up, I would like to make this clarification. Immortal time refers to person time during which, by design, death or the study outcome cannot occur. Or the study outcome is quite important to our appreciation of this bias, because what it means is that immortal time bias can impact any analysis with the inappropriate accounting of immortal time, regardless of whether the outcome is death, which it just so happened to be in my examples in this video, or something else. Ultimately, do not let the name mislead you. Everything we've discussed is applicable to any study outcome, not just death. And these concepts relating to the appropriate accounting of person time can be generalized to all exposures, not just treatments, which again just happened to be the focus of the examples in this video. Therefore, in conclusion, rates and hazards and rates and hazard ratios tell us how quickly something happens when comparing our exposed and our unexposed groups. An immortal time bias is the inappropriate accounting of immortal person time. In terms of misclassified immortal time, our rate in our treated group is biased or underestimated. And in the case of excluded immortal time, our rate in our untreated group is biased, but it's overestimated. And in either case, the rate ratio is biased or wrong. Both manifestations of immortal time bias can make a given treatment look beneficial when that treatment is in fact unhelpful or even harmful. Now, there are two very useful boxes in the Levesque et al. Paper. The first, box 1, is titled Common Manifestations of Immortal Time, and box 2 is titled Criteria for Identifying Immortal Time Bias in Cohort Studies. While I would encourage you to read this entire paper and the many other papers that exist on this bias, these two boxes allow you to have a quick understanding of how this bias comes to be and how you can detect it in your analysis and in papers that you are reading. I will simply read the first bullet point of each box in this video. Common manifestations of immortal time. Immortal time bias, or more specifically, immortal time, may manifest when the treatment is defined as at least one prescription dispensed after, for example, hospital discharge, when the discharge date represents the start of follow-up or cohort entry. Going down to box 2, criteria for identifying immortal time bias, you can ask yourself, was the treatment or treatment status determined after the start of follow-up or defined using follow-up time? In conclusion, immortal time bias is very frequent in the literature, and it can impact a variety of exposures or interventions, including but not limited to treatments, and it also impacts a variety of outcomes, including but not limited to death. There is a large detrimental impact of immortal time bias because these bias findings can and do lead to bad clinical and policy decisions. And Levesque and colleagues wrap up by saying that all cohort studies should be assessed for immortal time bias, where box 2 on the previous slide can help you do just that. And with that being said, thank you for watching this video on immortal time bias. If you would like to see similar content in the future, please subscribe to my channel. And of course, feel free to leave questions and comments below.